Welcome. Good morning for Organic Chemistry 2341. This is our 8 a.m. class on Tuesdays and Thursdays. Welcome back. Today we have two things. We're going to start our module 3, acids and bases, and then we're going to stop early for our activity for the day. So go ahead and either have a physical or electronic copy available to you, because when we break out into the breakout rooms, you'll need to have something. Eventually, you'll have to have something that you can upload to Canvas. So that's what I want you to do. Think about what you can do while we're taking notes here, that you can have something, either a screenshot or drawn out on paper, and just take a picture and upload it to Canvas, because that's what we're going to have to do to get credit for this activity. Okay, so I'm going to let a few more people in. And let me go ahead and start sharing my screen and pull up our chapter 3 slides. Screen share. Oh, I got to plug my computer in to my, okay. Let's see. All right. Do we see my slides? So I'm going to put all of the thumbnails over here on this side, and I'm going to leave the chat on this main page so that I can check for questions. Okay. Does it have to be a PDF? It does not. It can be a picture or a PDF. Anyway, PGNs, JPEGs, those work. TIFFs are a little big, but it can be any, I allow any uploadable file. So it can be an image file or a PDF file. I had a lot of people just take a pic on the phone and upload it from there. That works really well. I have an app actually that does that as well. There's a question here about turning pictures into PDFs. I actually paid for one called Scanner Pro, and it saves everything. It makes really good high quality PDFs, but that's not necessary. They're also recommending Genius Scan. What we need here is that we want to have it uploaded to Canvas by midnight tonight. Okay. All right. So we've done a lot. We've learned that electrons do the bonding. We learned that our Lewis dot structures tell us where the electrons are, and that where the electrons are tells us that we can have what shapes we have and how many bonds we can have to which atoms, right? So that hybridization tells us that. With that, we went on to nomenclature. We looked at all the different functional groups we had available to us. We learned how to name all those functional groups, and we learned the basic rules for nomenclature. We follow all those rules in order, and we should get to the correct name each and every time. Okay. I'm admitting someone here. All right. There are several other comments about free apps on the chat room, so take a look at that. Okay, so that brings us down to the next thing. Okay, acids and bases. You're thinking, acids and bases, we learned that in Gen Chem. Well, yes, you learned a kind of acid and base in Gen Chem. What I want to teach you is the concept of acids and bases we use most in organic chemistry. We have two things for that. One is called the Lewis acid base theory, and that is universal within organic chemistry. Then we also have the Bronstedlowry acid and base center, and that is used extensively and does not require water to be an acid or base like our traditional Arrhenius acids and bases. So that's why I want to redefine acids and bases in the context of organic chemistry. So the first thing I want to talk about is what we call a Lewis acid and a Lewis base. Okay, so this is different than what you're used to. What you're used to as an acid is something that has a hydrogen and gives that hydrogen away. I want to take that definition and put it on the shelf right now, and I want to tell you about a Lewis acid. This happens more often in organic chemistry than the other acids, and so I want to really, really drive home the concept that a Lewis acid is a substance that can accept a pair of electrons. Okay, now I'm going to show you that a Lewis acid is the correct definition for even one that transfers a hydrogen or even one that's in water. Lewis acid is the most broad definition for acid we can use. Okay, so a Lewis acid is something that accepts a pair of electrons. So think of something that is lacking electrons or has a positive charge. Lewis acid. The opposite of that, of course, is a Lewis base. That is a substance that can donate a pair of electrons. Okay, I want to add one little phrase to the end of each of those. A Lewis acid is a substance that can accept a pair of electrons to make a sigma bond. And a Lewis base is a substance that can donate a pair of electrons to make a new sigma bond. All right, so with those two definitions, let me run through some concepts where we are doing stuff where we're not transferring hydrogens. And that's why this definition is important. Okay, so the first thing I want to look at is this thing right here. We have water right here. And in a traditional sense, that water can give off a hydrogen and be an acid itself, right? But in this case, we're not using it as that. Okay, but we have boron. And boron has 6 valence electrons. It's typically happy doing that, and it's fine. That balances its electronic charge. However, it is electron deficient, and it doesn't have that full 8 electrons in its outer shell. Therefore, it can accept electrons. Okay, so what's our definition of Lewis acid? Our Lewis acid is a substance that can accept electrons to make a new sigma bond. All right, now let's look at the water here. The water has 2 lone pairs. This is pretty common to see in a Lewis base. You're going to see lone pairs or a negative charge. Typically, that negative charge is on a lone pair. Okay, one of the electrons of the lone pair. So in this case, our lone pair electrons are the electrons that are going to be donated, Lewis base donated, to make that new sigma bond. Okay, letting some of it in. So what does that mean? So what happens is I'm going to erase these right here. These electrons are reaching out to this electron deficient boron. Okay, the Lewis base is using its electrons to donate electrons to that Lewis acid that wants to accept the electrons to make a new sigma bond. Okay, now notice we have 2 neutral compounds, and when we do this, the oxygen now is lacking an electron and has a positive charge, and the boron now has an extra electron and now has a negative charge. Okay, now in a Lewis dot structure, we'd say, well, let's move stuff around so we don't have those, and that means that we can go backwards from that. We can actually break this bond and go back to our 2 neutral species. So we have a doubly charged species, which is not highly favored in our Lewis dot structures. That's why we have an equilibrium right here. And so when we have this equilibrium between going forward and going back, we're going to end up with an equilibrium constant. So it's going to lie somewhere in between, not 100% the Lewis acid Lewis base, but also not 100% that charged species. These slides should be on Canvas under files. Let me see. I'm pretty sure they're on Canvas. Oh, module 3 slides are not on there yet. Okay, so I will upload those right now so that you can see them. Sorry, I thought I already uploaded module 3 slides. And I know a lot of you like to follow along, so I want to make sure I use that. Module 3 slides to Canvas. I'm uploading to Canvas right now, so you should be able to find them as soon as they upload. It's a big file. It's like 25 megabytes, because there's lots of pictures in here. Okay, so I just added the module 3, and I'm about to publish it right now. Save. All right, so you should be able to find those on Canvas now. Sorry about that. I thought I'd already uploaded those. All right, so let's move back to our definition here. So there is an equilibrium available to us in the reaction between a Lewis acid and Lewis base. So the concept of acid and base being in equilibrium should not be a scary thing, The key here in our Lewis and acid bases, we're making that new sigma bond with those electrons of the base, and the Lewis acid is accepting those electrons from the Lewis base. Okay. Let's look at that in a different one where it doesn't form a charged large molecule. And in this case here, we have a negative charge. So again, look for negative charges or electron pairs in our Lewis bases. Now, we're going to look at this right here, this bromomethane, as our Lewis acid. It wants to accept electrons. Why? Well, this is a polar bond right here. Bromine is more electronegative than carbon. Therefore, it's pulling some of the electron density away from that carbon, making it more electropositive. That means that carbon is our Lewis base, our Lewis acid. Our Lewis acid wants to accept electrons, and it has a reason to because of that polar bond with the bromine. So what can happen is our electrons will reach out and create a new sigma bond. This is our new sigma bond here. But what also happens is that the electrons from our sigma bond already start to leave and stay on the bromine. Okay, so think about it. Bromine's an electronegative atom. It doesn't mind having a negative charge. So this isn't a big energy thing to make this happen. However, now that you have a negative charge on the bromine over here, it is now your new Lewis base. And because you have a polar bond between your sulfur and your carbon, it can actually go backwards. So now your products are a new Lewis acid and a new Lewis base. Okay, so, but notice the carbon center here was always the Lewis acid, and these things with lone pairs were always the Lewis base. And of course, it goes in some kind of equilibrium, and so the which way it lies is going to give us an idea of how our equilibrium constant is going to tell how far it or away it goes. Okay, questions on Lewis acid. Okay, I can compare this exact definition of acids and bases to all other types of acids and bases. It's true. Okay, think about adding HCl to to water right here. What's going to happen is the lone pair in your water is acting as the Lewis base. The hydrogen here is acting as the Lewis acid, and it gets transferred to that to create a new sigma bond to form hydronium ion in a counterbalancing negative charge. So do you see how that traditional definition of an acid in water is exactly the same as Lewis acid and Lewis base? In this case, the water is acting as a Lewis base because of the lone pairs. Water can also act as a Lewis acid if something else wants the proton more than it does. Okay, so really kind of start looking for these concepts of those lone pairs as bases and those electron deficient atoms. Try to figure out which one is the most electron deficient atom. And you might even just use bond polarity to help you find that. All right, questions on acids and bases? Okay, no, lots of head nodding. Okay, and nobody in the chat. So I'm going to go ahead and move to the next slide. Okay, so that's a definition that'll work with everything we have here. However, a lot of times in organic chemistry, we do transfer a proton. Okay, so I want to introduce a second definition for acids, but we call them Bronstedlowry acids, okay, and bases. The thing about Bronstedlowry acids and bases is that they do transfer a proton, but they don't always make hydroxide, okay? So in that case, we are looking for a slightly different definition. Our acid is a substance that can donate a proton, okay? So it can give a proton away, okay? Our Lewis base is one that can accept a proton, typically forming a sigma bond, and there could be a change in charges here, but a Bronstedlowry acid donates a proton. A Bronstedlowry base accepts a proton. So that's that's much closer to our definition of acids and bases we learned in Gen Chem. So in this case here, we have, this is acetic acid, And I said that acetate group is going to become very important here because we're going to use it a lot. So this is acetic acid right here, and that acetyl group is very important. And so it has this acidic proton on it right here that it can give away. It can donate. Okay, so it's our Bronstedlowry acid. Okay. In this case, we have our hydroxide ion as something that's going to accept that proton. Okay, and it's going to accept that proton by using its electrons to reach out and grab that hydrogen, breaking the bond, the sigma bond between the hydrogen and the oxygen, and leaving those electrons on the original compound. That's where we get this negative charge. And it now has donated its proton. And we have accepted our proton in this right here. So, did you see something interesting? The acetic acid was the acid on this side, and the hydroxide was the base on this side. But as soon as they exchange that proton, they now are actually looking like the opposite of what they were before. Look over here. This now has the negative charge. It's now a base. This now has a proton it can donate. It's now the acid. Okay. And we have a term for this. We call this conjugate base and conjugate acid. So if we have an acid on one side of the reaction, it becomes the conjugate base on the other side of the reaction because it converted from the acid to the base, so it conjugate. So we now have an ability for that conjugate base to accept protons. Same thing happened with the acid. We started with the base and it became the conjugate acid. We now have a proton we can donate. This pairing, this acid conjugate base pairing and base conjugate acid pairing is very important for understanding our equilibrium between them right here. Okay, so Bronstedlowry acid is something that can donate a proton. Bronstedlowry base accepts a proton. When an acid donates a proton, it becomes a conjugate base. When a base accepts a proton, it becomes a conjugate acid. Okay. So why do you care? Okay, well, you care because it tells us something about the whole concept of why reactions move forward, okay? Reactions move forward because they want to go from the stronger acid and or base to the weaker acid and or base, okay? Even if they're in equilibrium, the equilibrium will shift to the weaker acid or weaker base, okay? So, and the way we think about that is the stronger base always will win the tug of war with the proton most of the time. Notice I said most of the time because we still have an equilibrium. In the case where the equilibrium forward right here to this condition is much, much higher than the back one, it's going to be shifted more toward this side. So we're going to have more of these products and fewer of these products, okay? And the reason it does that is the hydroxide ion here. Let me actually do it right here. The hydroxide ion is a stronger base than the base on this side of the equation. Okay, so if the hydroxide's the stronger base, that means the reaction is going to be shifted more toward the weaker base. Okay. The other thing we can look at is if we have the stronger acid is always going to be transported to the weaker acid as well. Okay, so in this case, these are both the stronger acid and stronger base going to the weaker acid and weaker base. That's the driving force to drive it to products. Okay, so let's talk about that a little bit in the function of, like, when we did water-based acids and bases, we talked about pKa's, and we talked about the pH of the solution. The pH of the solution is the natural log of the equilibrium constant between the hydronium ion and the hydroxide ion, right? So that is how we got to the idea of how acidic something was by taking that natural log of the equilibrium constant, and that gives us a range from 0 to 14 in the presence of water because of the strength of the hydroxide ion and the hydronium ion. I have a question. Is there an instance where the acid and base could be pulled in opposite directions? Um, you will always go toward the weaker acid or base in all these reactions. That it'll be drawn to that side. The equilibrium will be shifted to that side. It might not go 100%, but it's definitely going to lean toward the weaker acid and base. Okay. So in our previous work where we had a water in our system, we looked at the Ka is the equilibrium constant to figure out how it's shifted here based on the amount, the concentration of our conjugate base times the concentration of our proton, I'm sorry, the proton here, this conjugate base, and the over the concentration of the acid here. And we can do the same thing for base too. We can actually measure the base strength of it by looking at the hydroxide ion concentration, the conjugate acid concentration divided by the base concentration here. And that will give us the same scale of 1 to 14, but that's how strong the base is. Okay. So if we take this equilibrium here, that means the stronger this is, the higher the concentration of this material, that means the weaker the acid is because you have more of that there and less of it in the upper level, which means that a strong acid will have a low pKa. Okay, it has a high equilibrium constant. It has a high concentration of hydronium ion, but that means it has a low pKa. So think about your very acidic solutions are 0 to 7, right? That means your weak acids are going to have slightly higher pKa's up to that 7, okay? And bases do the same thing. A strong base is gonna have a lower pKb, which is base, and the weaker bases are gonna be above that strong. And the cool thing is, in water, turns out pKa plus pKb is equal to 14. So you can always get back and forth, okay? So, but that only works in water. Notice that water is in both of these equations. In Bronstedlowry acids, we don't have to have water, so we have to have a different measure. And we call those the equilibrium constants of the acid. And so from that, we end up with what we call a pKa, which is, instead of pH, it's just the equilibrium constant of the acid. Okay, so let's look at this series of things, and I'm gonna focus on the pKa's right here. The pKb's right here are also calculated, but notice that it is also off by 14 points from this. You can actually get these here. But on the water-based system, our top was 14 for the base and our bottom was 0 for an acid. Because in organic materials, we're not limited by water, we can go above and below that 14 number. Okay, so let's look at this series of pKa's for these organic compounds. Okay, so we're going to look at this column here, and we're going to talk about the relative range. So before, when we had a strong acid, that was the closer it was to 0, the stronger it was. Okay, and so that means that things like this, where it's really close to 0, make it a strong. Let me do red so it'll show it better. Right down here, this right here is really close to 0, so we're going to call that a stronger acid. However, in the case of the Bronstedlowry series, this pKa series of organic compounds, in the absence of water, we can actually go below 0. For example, the hydronium ion is -1, and we have a lot of the acids like HBr, HCl, and HI are actually negative numbers. Okay, this is because our equilibrium constants can be shifted very much more so than in the presence of water. So we call anything right here very strong acids or anything below 0, and then they start getting weaker and weaker as the number comes up. Notice on our previous scale, we only went up to 14. Right here on our non-aqueous version, if we have just a little bit of water in it in a different solvent, we actually have the water has a pKa of 15.7. Okay, and so that is a nice, interesting thing to remember. Okay, so I'm going to want you to remember a few of these pKa's so that we consistently compare things together. The first one I want you to remember is acetic acid. Okay, so in this case here, acetic acid is right here. It has a pKa of 4.8. Okay, it's one of the strongest organic acids we have. This is formic acid. It's a little bit stronger, but the most common acid we have in organic chemistry is that acetic acid, and it's 4.8 as a pKa. Okay, so as we go up with things with large atoms like sulfur, those are fairly acidic as well. Coming up to this ammonium salt is a 9. This phenol here is one you might want to remember because we're going to use it a lot. That proton is acidic, but it's not as acidic as acetic acid, but it's more acidic than water in organic systems. Now, water and alcohols, this ROH compound here, are about the same. They're right around 16, and that's a good number to remember, these two numbers here for comparison. And then as we move up, we actually can start looking at things that aren't traditional acids. And this is the hydrogen on a ketone that is adjacent to a ketone actually has, it can be pulled off, and it has a pK of 20. Okay. Once we go up to hydrocarbons, we can actually pull a hydrogen off of a hydrocarbon with a very, very strong base, and it actually has a pKa of 43. That would what you would traditionally think is not an acid, but you can pull off that hydrogen, and when you do, you use a very strong base. And when we have hydrocarbon, just only sigma bonds, we can actually pull one of those hydrogens off with also a very strong base. So in the case of this, our pKa's keep going up, keep going up, keep going up, and keep going up, keep going up. So we started out down here at the bottom with strong acids, very, very strong acids. Then we moved up to this middle range just above 0, where we had what we call our strong acids. Then we have this next zone here, which we're calling our weak Bronstedlowry acids. And then the last zone way up here is what we call our very weak Bronstedlowry acids. Okay, so knowing those boxed ones is kind of important for keeping these kind of in order. The other thing I want to draw attention to is that when you have a very strong acid, I'm going to pull up this end here and erase this. When you have this very strong acid, pKa is really close to 0 or below 0. Once you make them their conjugate base, they are very weak bases. Wait a minute. Okay, it was a strong acid because it really wanted to donate that proton. So if it really wanted to donate that proton, it doesn't really want to accept a proton because it was trying to get rid of it. So our very strong acids become very weak bases. Okay, so that is interesting that one very strong acid becomes a very weak base, which means that if we had a strong acid and we were donating it here, we actually went from a stronger acid to a weaker base. That's the equilibrium constant we're talking about. We're always driving to the weaker acids. So comparing our acid strength on one side of the reaction to our acid strength on the other side of the reaction. Okay. Now let's take this up again. Our weak acids right here become strong bases. Okay. So things like water to hydroxide, hydroxide's a strong base, right? We do the same thing with alcohol. We remove the proton from alcohol. It's a strong base. But look what happens when we have very weak acids. We end up with very strong bases, okay? Which means once we pull that hydrogen off of a hydrocarbon, it will try to react with everything in sight because it's such a strong base, okay? So when you have things like this, very strong reactive species, a very strong base, it's going to try to become the weaker base whenever possible. Okay, so that's our driving force in this Bronstedt-Lowry system. And the concept of a weak acid becoming a strong base is very important. And a very strong acid becoming a very weak base and a very weak acid becoming a very strong base is very important to knowing which way the equilibrium lies. Okay, 30, I want to stop at 8:45. All right. So let's look at just a few of these in select order here. We're just going to look at the acid right here. And the pKa of this acid, HCl, is -7. So it's less than 0. It's a very strong acid, okay? Which means that its conjugate base, when you remove the proton, becomes that chloride ion. That chloride ion is a very weak base, okay? Strong acid, weak base, okay? Let's go to water, or acetic acid right here goes to acetate ion, and it's also a weak base. Water has a pKa of 15, and we go to hydroxide, which we think is a decent base. It's a strong base, right? So just shifting this amount, we go from a weak base to a strong base. Alcohols, when they deprotonate, become alkoxides. That's the charge on the negative on the oxygen on alcohol, and they are strong bases too, about the same as OH. Now let's look at the hydrocarbons here. Okay. sp1 hybridized carbons are the most acidic. The hydrogen is most acidic on those carbons, and we have a pK of 25, which gives us a strong base, because it's stronger than hydroxide, of that acetylene ion, acetylide, right here. So that's our sp1 hybridized carbon has a very acidic proton. In just hydrogen by itself, if we're pulling it off as a proton, that's going to leave a hydrogen with a negative charge on it. That's a pretty darn strong base. And we know that because our pKa is higher than that of the acetylene. We go to this nitrogen. We have a slightly more polar bond than in carbon, and it's a sigma bond, but it's very weakly acidic, and makes a very strong base. This is the amide ion, and we're going to use that to deprotonate things. Okay. Now, once we have acetylene, our pKa jumps again, making it an even weaker acid, but that makes it an even stronger base. And at the end here, we have methane. If we pull that hydrogen off at 50 pKa, we have this carbanion, that we have a negative charge on carbon. That's one of our strongest bases we're going to use in organic chemistry. Okay. So what we're looking for is that this juxtaposition that a very strong acid becomes a very weak base, and a very weak acid becomes a very strong base. All right, questions on that? Okay. And this is all within the Bronstedlowry definition of acids, because we're transferring a proton. Okay, so now that we have this juxtaposition of a strong acid becomes a weak base, and a weak base becomes a strong acid, how can we use that to help predict the value of our system? Well, the cool thing is you could say, well, one's the acid, one's the base, so I can get the pKa and the pKb and compare the pKa to the pKb. But you don't have to. All you have to do is compare the acid strength of the two components on either side. Okay, so let's look at this reaction here. In this case here, we had acetic acid as our acid here. We have our hydroxide as our base, our Bronstedlowry base, or our Lewis base. It has electrons. And it's going to react to give us our conjugate base. This is our conjugate base, and our conjugate acid here. Okay. So the only thing we have to do to figure out which way the equilibrium is shifting is look at the pKa of the acid on one side of the equation and compare it to the pKa of the acid on the other side of the equation. Okay, so the other thing we need to remember is the lower the pKa number, the stronger the acid. So let's look at what we got here. On this side of the reaction, we have a pKa of 4.75. Okay, and on this side of the reaction, we have a pKa of 15.7. So 15K.7 is bigger, which means it's more acidic or less acidic?
Less.
Less, right. Remember, the higher the number, the less acidic it is. So because our less acidic one is on this side of the reaction, that means the equilibrium is shifted to this K. Is it shifted there 100%? No, there has to be a very large difference in that to make it happen. And I'm not going to give an actual value, but the bigger the difference between the pKa's of the two acids, the bigger the shift is over. You have to have a very large difference to have 100%. Most reactions have a little bit of play in them, but they don't. Okay. So in the case of this, where our pKa's are only about 10 apart here, and we have an equilibrium right here. If we get a slightly larger difference here, let's say we've deprotonated acetylene, that sp hybridized carbon, and we're using it as the base. It can deprotonate water, which has a pKa of 15, and we look at the acid on this side is now acetylene, and it has a pKa of 25. So that difference is also about 10. Okay, but we know which way it's shifted because it's much less acidic. So the idea is if it's greater than 10 and much less acidic than the other component, you're going to tend to shift it almost completely over. There still is an equilibrium here, but it's so small, it's almost not measurable. Okay, so the driving force in these reactions is to produce the weaker acid and weaker base. Okay. So now, using this Bronstedlowry and the pKa's, we can find the acid strength on one side of the equation, the acid strength on the other side of the equation, and compare them to figure out what happened. Okay, so let's apply this to organic chemistry. Okay, so when we apply this to organic chemistry, we always have to think about our acid-base pair. Most of the time, we don't use water, and so if the reaction is in water, we don't show water. Okay, so it's kind of like making your half reactions in Gen Chem. Okay, so in this case here, we're going to look at a Bronstedlowry acid, but it also follows our Lewis acid-base rules in the comparison here. So in this case here, we have, this is our Bronstedlowry acid because it's going to accept a proton, but it's also a Lewis base, a Bronstedlowry base because it's going to accept a proton. And it also has two lone pairs, so it's also a Lewis base. Okay. In this case here, we have our acid. It's going to donate a proton. Okay. So that means these electrons are going to reach out, creating a new sigma bond, giving us our conjugate acid. And the electrons that were in between here are left behind, giving us our conjugate base. Okay. Every reaction we do where we transfer a proton, we should be able to find the acid and the base on one side of the reaction and the conjugate base and the conjugate action on the other side of the reaction. You just need to get used to looking for which one's which. Okay. So let's talk about the mechanism here. So I said before, if we look at it from a Lewis acid perspective, we can follow the mechanism very clearly. We have our Lewis base has electrons to donate to make a sigma bond. Our Lewis acid has a electron deficient element that can accept those electrons. So in this case here, our Lewis base is reaching out to get that electropositive hydrogen. And it's electropositive because typically this is a polar bond. You have a more electronegative atom here. And when you do that, the sigma bond that was between that acid and that proton goes and resides on that conjugate base as a lone pair, and typically a negative charge. Now, when that happens, we now have our new sigma bond with the proton. Now we have a charged species because we've used one of those electrons to make that new sigma bond. Okay, and it's shared. It's not wholly on the oxygen. Okay, so now we have something that is positive and it has a proton to transfer, so it's its conjugate acid. Okay. So now that we know that this Lewis acid base is going back and forth by sharing these electrons, by looking at the strength of the sigma bond, we will know that we which way the proton will go, okay? And the stronger bond is the less polar bond, which means the weaker acid-base pair, the weaker acid is going to be the stronger bond, okay? So remember, acidity, it will have to do with the polarity of that bond. The less acidic it is, the stronger a sigma bond it has. Therefore, we will always go toward the weaker acid or the weaker base when possible. Okay. So, but the acidity depends on the stability of that conjugate base, okay? So if that conjugate base is something that doesn't like having a negative charge on it, it's not going to be very stable, okay? And if it does like having a negative charge on it, it's going to be stable. So let's think about that one as HCl right here, okay? And we see that that's a strong acid, right? It's a strong acid because when we transfer that proton, our conjugate base is the chloride ion. And the chloride ion is very stable. It likes being a negative charge. It likes just having that negative charge. It's one of our very common ions. So think of it as this is such a strong acid because this is such a stable conjugate base, okay? So if we have a less stable conjugate base, then it's going to go to if we had a less stable conjugate base, it would be shifting back toward and being less acidic. Halogens like being more negative. Yes, halogens can stabilize a negative charge because remember, the electronegativity of the halogens our electronegativity increases as you go up and over, with fluorine being the top, chlorine, bromine, and iodine, all having very high electronegativities. They want those electrons. And we also have a thing about size. As these get bigger, we can spread that electron density out over a wider range. So that's why all of these ions like to form ions, because they can stabilize that negative charge. Okay. All right. Always think about the equivalent where the strong acid increases hydrogen ion concentration, which means it's shifting toward the more stable base, the more higher concentration of the stabilized conjugate base. Okay. So the whole concept here is the idea that we are going to look at that equilibrium constant between the base of the conjugate base, conjugate acid and conjugate base over the concentration of our original acid right here. And again, we ignore water in this because it doesn't have to be water. And so that gives us that equilibrium. We're always going to find out that the higher concentration of this you have, the lower concentration of these things you have. And so that number goes down. And the opposite is true. The lower concentration of this, the higher concentration, and the pKa goes down. Wait, hold on, did I say that right? The more higher concentration of this, the weaker it is, the higher the concentration of this, the stronger it is. Yeah. The number goes up. Yeah. Sorry. All right. So when thinking about something, the stronger acid is the one with the lower pKa number. And therefore, you want to shift to products with higher pKa numbers. That way, you'll know that you have shifted to the less acidic compound, and that's why we move in that direction. So what makes the conjugate base stable? Okay. So let's talk about that. The conjugate base is more stable when it can stabilize that negative charge. Okay. So the factors that influence that, we have 4 factors that influence that, and we're going to talk about that next time because I need to break for our activity. Okay, so we're going to pick up right here at the 4 factors that affect the acidity or the conjugate base, the basicity of the conjugate base next time. So I'm going to mark that on my slide, start here, slide 14, and I'm going to pull that off. Okay, now what we're going to do now is we're going to get ready to do our activity. So the first thing I want to do in the activity is I want to pull up the organic nomenclature review, a PDF from the Canvas site. Okay, so this is a very great thing to help you remember. It has all the different functional groups right here, and like how to name them like that. The different types of hydrocarbons we have. We've talked about our saturated hydrocarbons, including alkanes, alkenes, and alkynes. We've put off arenes. This image is from a different chapter, so don't go to those chapters. I mean, books. So we talked about our alkyl groups, and then we have our basic rules of this. These are the rules we went through on the last few slides. They're just enumerated in a single place for you to make it easier for you to follow. And then it also goes for some other things like higher priority. So amino, alcohol, these are our priorities. It reminds you about the substituent, prefix, infix, and suffix right here. Reminds you about the nature of the carbon-carbon bonds, the different common class names. It also does degrees of carbons, degrees of alcohols, and we haven't talked about, well, we did talk about the degrees of ammonia. The degrees of amines are different than the others. Amines and amides are how many carbons are attached to the nitrogen. Okay. Okay. So, and then there, you'll learn there's some other rules there for the thing. And then down here at the end page, this is a summary of all the functional groups you're going to encounter in organic chemistry and organic chemistry 2. So it's really kind of interesting to look ahead and start looking at these. I have the name, these functional groups right here, and they're listed from the lowest priority. So is it going to change the name to the highest priority way up here? And what they would be called are on the suffix name here. If they're a substituent on a higher priority thing, this is what the prefix would be. And then I showed you what the general structure is. Anytime there's an R, it just means there's a carbon bond there. If it's actually explicitly spelled out, that means you have to have that group on there. For example, on this one here, the thiol is the one with the hydrogen and the sulfur on it, where the alcohol is the oxygen and hydrogen on there. And it's a sulfide when you have two R groups here, but it's in the same area. So that's how to use that table, and that's where to go. So let me go ahead and go briefly over the 8 rules again, because we're going to be using these extensively. The first rule, I like to call it rule 0. Yes, that is correct in the chat room. That is where you find them. They're on Canvas under files. Find the functional group and its priority. Okay, so if it's an alcohol, then that's the highest priority. You're going to name it for that. Then you have to find the longest chain containing that high priority group. Okay, and remember, it can be in a circle. It doesn't have to. I'm sorry, not a circle. It can be in a really wiggly chain. It doesn't have to be straight. Then you look for branches. You put the parent chain on the longest carbons. You give each substituent a number. You want the substituent to be lowest if possible. If you end up with 2 substituents that are coming down to the same number, you figure out which one has the lowest alphabetical number. Then you put it in order. If there are 2 or more identical substances, you can use di, tri, and tetra, but they don't count toward alphabetization. If there are 2 or more different, you put them in alphabetical order. And you put the number at the end of the chain to give you the substituents encountered to the first. So you number it so that you get the lowest number possible. Then remember our E and Z rules. Don't worry about R and S. We're not going to do R and S yet. But the E and Z are things you do have to prioritize in this particular one. Right there. And then in chapter 5, we'll learn the R and the S. But luckily, it's the same priority rules. All right. Any questions about this organic nomenclature review? Okay. All right, now I'm going to pull up the exercise right here. Let me stop sharing my screen and go ahead and get out the activity. If you can find it, I'm going to pull up the one that's on Canvas right here, and I'm going to share it real quick. Okay, so here are your instructions. Okay. What I want you to do is to work in groups of 5. I'm going to break you out into breakout rooms. You can either turn your cameras on, or at least unmute yourself and start talking about this. I want you to work together to start naming all of the structures that you see on here. And I'm going to open Google Chrome files. You should be able to see that group activity. So on the first page, I want you to name the following compounds and put the name in the box. Okay, so use all your rules. Find the highest priority thing, find the longest chain, do all of those things, find the lowest section. And you got to remember some certain rules, like if you have an alkene, you want the alkene carbon to be on the lowest possible, number. So you need to follow all those rules. We have one bicyclic compound. This is the same structure, just in 2. You want to name those. And then what you'll see in this structure is you're going to start to see the priority change as you go up. So you have to figure out the highest priority group based on that table and get those there. So fill all those out as a group. Start working through it. Talk through your thought process. You want to talk through your thought process. Make sure you have all the steps in the right order. And don't just say this is how it is, we're done in 5 minutes. Talk through it so everybody gets a chance to talk through. Not able to see anything on the shared screen. Let me share it again. Let me share my screen again. All right, can we see it now?
Yeah.
Okay, so the first half is fill in the name. Now the second half is the opposite. What I want you to do is to take the name and start drawing the structure. Obviously, you want to have a scratch piece of paper for this first, and then you can start drawing out the structure for all of these. And so when you're done, go ahead and take pictures and upload them to Canvas. While we're here, I'm actually going to come out of this. I'm going to go back. So in Canvas, under assignments, right here, you should see under group activities, group activity 1. It's due. Actually, this one is not your, this is not your class, but there, let me go to your class. It's due on the wrong day. Go to assignments and down to activities. Yeah, okay, I need to change the activity date. And you'll go here and it'll say upload file. And so you can upload the file, and I can take anything as a file on this. Just do it by midnight tonight.
So if we don't finish it in class time, we can finish it on our own?
Correct.
Okay.
Try to get as through as many as possible in class time, so you can get that help, that team spirit help. And then what you can't do is, I gotta change this. It's due today. Not everyone due today. Done. All right. And so you can upload any files that you want to do that. Okay. Questions about the instructions? I'm going to stop sharing.
Are you going to come around to the breakout rooms if we have questions?
Yes. There's a couple things in the breakout rooms. There's going to be a whiteboard. You can put it up there and start sketching on there, or somebody can pull up their screen. You can share screens. Be polite and be nice to each other. And then there's a button there to ask me to come to your breakout room, and I will circulate through the breakout rooms as needed, or as quickly as I can.
Thank you.
It takes a couple of minutes sometimes. Okay, so right now we have 82 participants. So I want to break us out into, let's see, how many breakout rooms? Let's see, I think 5 to 6. Let's go with 5 to 6 participants per room, and you're just going to be randomly assigned. So the first thing you want to do is kind of introduce yourself and say, okay, hi, let's, I can pull up my screen, or can somebody pull up their screen? And then just start with number 1. Say, well, what's the first rule? What's the second rule? Go through the entire process with each of the things, and you should get to the correct answer. Okay. So there's going to be 14 breakout rooms. So it might take me a little time to get and answer your question, but I will stay here through the 9:20. Actually, I'll probably stay here until 9:30. So you can stay in your breakout rooms until then. At 9:30, I will go ahead and log out. You can stay in your breakout rooms as long as you want, or you can just leave at that time. Okay. Questions about instructions? All right, I'm going to go ahead and start. What's going to happen is it's going to say, do you want to join your breakout room? You hit join and you go in and start talking. All right. See you soon. Okay. Breakout rooms are open. Okay. Yeah, Sheila, what I found is I thought you could actually go and jump out in different breakout rooms, but what ends up happening is I can't seem to do that. I don't know why.
I think like maybe for future you could put me as like a co-host and I should be able to jump around.
Okay, I thought we
So,
tried. Let me see if I can. I should be able to make you co-host now, but I think there was, yeah, make co-host. So see if you can go ahead and do that.
Yep, I can go into different rooms now.
Okay, great. I have a question in breakout room 1, so I'm going to head over there right now. Thank you.
Cool.
I'm stuck.
Oh,
Hi.
okay. Go ahead.
It says that you disabled screen sharing.
Oh, no. Breakout room. Let me screen share. Multiple participants can share at once.
Okay, yeah.
Okay, so that, can you share now?
Yeah.
All right, great. Let me go ahead and leave room, and I'm gonna head over to somebody else. It has probably